Hi, good day to each and everyone. For today's discussion, we shall be focusing ourselves on the concept of weight, normal force, and of course the force of gravity in relation to the dynamics of Newton's laws of motion. So grab your pens and your notebooks and get ready to take down notes as we are about to embark another moment of science with Mr. Rabino. Now, for this discussion, we shall focus ourselves on the concept of weight, force of gravity, and the normal force. Now, before we dive into the intricacies of this concept, let's try to recall first the concept of free fall motion. It was Galileo Galilei who actually established the concept that regardless of the mass of the object, all of them will fall at the same rate of acceleration, in which we know that g is equal to 9.8 meters per second squared, which is the acceleration due to gravity constant. Now, this means that all objects will fall at the same rate of acceleration, which is equal to 9.8 meter per second squared. Now, we might ask ourselves, what kind of force or what force caused this object to accelerate at this rate? So, we know that, of course, the answer for that is our planet Earth. And, of course, using the understanding of Newton's second law of motion, which is the law of acceleration that relates the quantities of force, mass, and acceleration, we can use this one to set up an equation for our force or for our gravitational force due to the acceleration of the objects due to the gravity, wherein F is equal to ma, wherein mass is m and a is for acceleration. But instead of using a here for this case, we will use the gravitational acceleration constant, which is g. So therefore, we can set up and rename some of these quantities. I'm going to refer to the gravitational force as F sub g, which is equal to m times your g, or your acceleration due to gravity constant. And this is actually equivalent to the weight of your object. Okay? So therefore, if you want to get your weight, all you need to do is just multiply your mass to the gravitational acceleration constant. So regardless of whether you are falling or not, this gravitational force is always present in our object, regardless of where, as what I've said, regardless of you are falling or you are at rest. But you might wonder, for example, if I'm going to draw a box here, for instance, let's just imagine that this box is at rest and lying completely flat on a level surface. For example, let's just imagine that that's a level surface. So what I've said, this gravitational force Fg is always present, right? So Fg is equal to mg. Now you might ask yourself, if the gravitational force is always present, then why is it that objects are not moving? Well, we can somewhat think of it this way. Since objects are at rest, always recall that Newton's third law states that in every action there is always an equal and opposite reaction. So therefore, there must be another force that exists that counteracts this gravitational force experienced by your object. And this counteracting force that opposes this gravitational force of your object is what we call as your contact force. Okay? And this contact force here opposes this gravitational force, making the forces balanced, so that the sum of all the forces here, your F here, is equal to 0. So, of course, we know that if the sum of all the forces is equal to 0, then the object will remain to be at rest or in its initial state or condition. Now, one type of contact force that we can describe here is what you call as the normal force. Let me just label this one here in our box, F sub n. That is what you call as your normal force. So F sub n here is your normal force. So therefore, you can always think of it this way, that your normal force, if the object is resting on a flat surface, that your F sub n is always equal to the gravitational force, which is of course equal to mg. So let me box this one so that you won't be confused. So therefore, your normal force and your gravitational force is actually equal if the object is actually lying on the surface completely at rest. Now, you might ask yourself, is the normal force always going vertical, or does it always lie on one dimension only? Now, your normal force is actually dependent on the position of your object, and it doesn't have to be always in a vertical dimension. For instance, let's just consider this example here. Let's just have an example here. For instance, I have here a wall, a very thick wall, a very sturdy wall, wherein if you push this wall, you cannot move this. So, for instance, you're going to apply a force going towards the right direction here, which in this case, I'm going to call this one as Fp. So, the force applied on this wall is on the horizontal dimension. So, therefore, the normal force also is exerted on the horizontal dimension. But in this case, it is going on the opposite direction. Okay? So, in this example, that normal force is not actually always in the vertical dimension. Or, for instance, let's just say that this is example number 1. For instance, here I have an inclined surface. Okay? Just for instance, I have here an inclined surface, and of course we know that there is a force exerted on this particular direction. So therefore, our normal force is also exerted on the same direction as this force here. Okay? So your cue here is that your normal force is always perpendicular. Always perpendicular to your surface. Perpendicular to the surface, regardless of the position of your surface, whether it is flat, it is vertical, it is horizontal, or it is inclined. Your normal force is always perpendicular to your surface. Okay? Now, let's set here some very simple examples and thought experiments. So, for instance, let's consider this example here. Let's just say, let's imagine that there are 3 cases of boxes here. First is for the box 1. We will imagine that this box is only completely lying on the surface, meaning it is completely at rest. Then, this is, of course, this is at rest. And of course, for case number 2, this is still at rest, but we will make a case that this box is being pushed downward with a force which I will call as F sub P. Let's just say 40 newtons, for instance. And then let's have box number 3 for this next example here. Now, instead of pushing the box downward, we will try to lift this box with a force which is still equal to 40 newtons. Okay, but for case number 3, we lift the box, but we don't actually somewhat lift the box completely. We are lifting the box, but it's still lying completely flat on the surface. But the but the force that you apply in trying to lift the box is 40 newtons. Okay. Now, of course, let's set the box mass, let's just say, to be equal to around 10 kilograms. Okay, so this box here weighs 10 kilograms, and this box also here also weighs, this box also here should also weigh around 10 kilograms. Now, for each of these case, what we will try to find, we will find the normal force for case number 1, for case number 2, and for case number 3. So let's try to, of course, solve all of these examples. So let's go for case number 1. So for case number 1, this is actually relatively very simple because according to the example, the box is just completely lying on the surface, which is of course flat. Okay, so therefore before you solve this, you need first to create a free body diagram of all the forces that are acting on this box. First is, of course, we know that the box is just lying on the surface, no other forces there, but instead we have your downward force, which is your Fg, which we will set as your m times g. Okay, and of course we have another upward force, which is of course your normal force. Okay, now in order for us to calculate the normal force here, you need to remember that all the forces here are acting on the y dimension. So therefore, the sum of all the forces in the y dimension is equal to the sum of all the forces acting also in the y dimension, in which in this case Fg plus F sub n. Okay, and substituting the variables, F sub y is equals, you know that mg here is mass, which is 10 kilograms times 9.8 meters per second squared plus Fn. But take note, since Fg here is going downward, so therefore we have to designate a negative sign in this case, okay, because the gravitational force is always pointing downward. So therefore, by the way, we forgot another equation here. This should be set to 0 because the box is at rest. I mean to say the net force there is equal to 0, or the sum of all the forces in the y dimension is 0. So therefore, if I'm going to calculate that one, 10.10 times 9.8, that is this is negative 98 newtons, okay, plus Fn, F sub n is equal to 0. Now if I'm going to transpose the other variable there, that will give me Fn, which is equal to 98 Newton. So therefore, our answer for number 1 is, of course, our normal force for case number 1 is that it is 98 newtons. So it's the same value as that of the gravitational force, only that its direction is pointing on the opposite way. Okay, so that is for case number 1. So for the second case here, we said that the box is being pushed downward with a force of F sub P, which is equal to 40 newtons in this case. I will encircle that. And of course, we need to label all the other forces that are acting on the box. We have, of course, our F sub G, which is the force of gravity. And of course, we have our normal force in this case going upward. Now, we need to add up all the forces in the y dimension so that we can create an equation for our normal force. So we know that the force, or the sum of the forces in the y dimension, is equal to F sub n plus Fg plus Fp, which is equal to 0 because the box is still at rest. So therefore, the net force should be 0. Now, we need to find F sub n in this case. So therefore, if we want to find F sub n, then we first substitute all the given values here. F sub n is still unknown. That's the one that we are going to find. Plus, we know our Fg, which is negative 98 newtons in this case. Plus, our F sub p, which is of course also negative 40 newtons because it's going downward. So therefore, the direction is negative. So that is our equation there, which is equal to 0. Now, transposing these values here, we will get Fn, which is equal to 98 newtons plus 40 newtons. So therefore, our F sub n here, adding up all these values, would be equal to 138 newtons. So this will be our normal force for the second case. Okay? So, let us now move on to the third case. Now, for the third case here, we have a box still with a mass of 10 kilograms, and this box is now being pulled up with a force which is equal to 40 newtons. But since the force applied by the person, 40 newtons, is less than the gravitational force, which is equal to mg, which we know that this is 98 newtons, therefore the box would still be lying flat on the surface, because, so what I've said, 40 newtons is less than 98 newtons, so it's still lying flat on the surface. Okay, so and of course we still have our normal force there moving up. So there are still three forces here, your F sub n, your F sub p, and your Fg. But this time, it would be a little bit different, because right now, the sum of all the forces in the y direction, F sub n plus Fg plus Fp, is still 0. But, take note, your F sub n right now would be plus, this is still negative 98 newtons because of the gravitational force moving downward. But your Fp right now here is now positive, since it is being pulled up. The direction of the force is going upward, so therefore this will be a positive number, so 40 newtons, which is equal to 0. So not transposing the variables will give us an answer which is equal to F sub n is equal to 98 newtons minus 40 newtons, and we know that 98 minus 40 will give us an answer which is equal to 58 newtons. And that is our final answer for these particular cases. Now, what if, for example, we will add another case wherein, what if, for example, for this box, I am going to lift this up such that the mass is still 10 kilograms, but I'm going to lift this up, but in such a way that the force that I will apply here would be greater than the gravitational force. Let's just say, well, this is 100 newtons, and now, of course, our F sub g here is still equal to mg, which is, of course, we know that this is 98 newtons. Now, what if, of course, the applied force would be greater than the gravitational force? Then we know that there would be a net force upward, so therefore the box right now will be lifted up and it will not be lying completely on the floor right now. In this case, our normal force right now here would be equal to 0. Okay, so therefore our sum of all the forces in the y direction right now would be only F sub p plus F sub g. So therefore this is of course, this is sub y would be F sub p right now would be 100 newton minus 98 newton. So therefore, there is a net force in the y direction which is now equal to 2 newtons. So therefore, the sum of all the forces here in the y direction now would be 2 newtons. So therefore, there is a net force upward of 2 newtons for this case. And those 4 examples shows you how the concept of weight, force of gravity, and the normal force would help us understand the dynamics of Newton's laws of motion and its application. The next example will show you how an apparent weight loss can be experienced while you are riding in an elevator. Now let's look at this another problem involving the concept of what we call as apparent weight loss. Let's read the problem. A 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g downward. She stands on a scale that reads in kilograms. So letter A, during this acceleration, what is her weight and what does the scale read? And letter B, what does the scale read when the elevator descends at a constant speed of 2 meters per second. So there will be two problems that we need to solve for this particular case here. But before we are going to deal with this solution, let's first draw a free body diagram of this problem. So first, let's draw a diagram here. Allow me to just use a black pen for this. So the diagram here is like this. A woman was riding, and oh, sorry for my drawing. So let's just imagine that this box here that I am drawing is the elevator. So let's label this. This is our elevator here, okay? And that the elevator, we know that it's in the problem, it's accelerating downward, okay? So therefore, let me draw a person here. So let's just imagine that this is the woman standing in the elevator, and let me draw a square so that this is the weighing scale that the woman was standing, okay? And it reads in kilograms. Okay, since this is a woman, so let's draw a hair, okay? So the woman is standing on a scale inside an elevator. So therefore, let's first identify what are some of the given variables in the problem. So we know that the given variables in the problem are as follows. We have the mass of the woman, which is 65 kilograms, okay? Then we have also the acceleration of the elevator. Allow me to label this one so that we can distinguish this to the acceleration due to gravity. So this is acceleration due to the elevator, which is around 0.20 g, meaning to say it's around 20% of the gravitational acceleration. So if we are going to designate a value for this, all we need to do is just multiply 0.20 times 9.8 meters per second squared. So therefore, our acceleration of the elevator is calculating that. Of course, let's use a calculator for that. 0.20 times 9.8, that is around 1.96. So therefore, we have our value for the acceleration of the elevator here, which is 1.96 meters per second squared. Let me box that one so that we won't forget this. Okay. And of course, let's not forget our constants, which is of course g here, which is 9.8 meters per second squared. Okay. By the way, all of this acceleration is moving downward. So therefore, this should be designated as a downward arrow for this case. So why am I mentioning that? It's because here we need, in our diagram, we need to draw the direction of all the forces that are being applied on the scale. So here we have, of course, the force of gravity on the woman as it is read from the scale, which is equal to Fg, which is m times g. And if we are going to calculate that, of course, that is F times mg, that is around 65 kilograms multiplied by your 9.8 meters per second squared. So don't forget to write the units, meters per second squared. So therefore, our F sub g here, or the force of gravity, or the weight of the woman itself, is equivalent to, let's use our calculator. Okay, so let's just use our calculator here. Okay, 9.8 times, times 65 kilograms. So that would be around 637 newtons. Okay, so 637 newtons will be the value of our force of gravity. Now that we have identified our force of gravity, which is of course equivalent to the weight of the person, which is around 637 newtons, it's time for us to also label the other forces that are acting on the scale. For instance, we have our normal force here labeled as F sub n, which is of course in this case pointed upward, because there's a force of gravity, then technically the normal force would always point upward. And also, we have also the force here due to the acceleration of the elevator, which is labeled as A sub E. So in order for us to calculate the force due to the acceleration of the elevator on that person, then we would need to designate an equation for here, in which the force here is equivalent to the mass of the person times the acceleration of the elevator. Okay? So now that we have identified all of the forces that are acting on the scale due to the person standing on the elevator, we can now create an equation that will help us get the sum of all the forces along the y direction, since most of the forces lie along the y-axis. So what I'm going to do right now is to write the solution for all the equations or all the forces that are acting on the scale. So this will become the sum of all the forces here on the y direction would be equal to the sum of the forces for the gravitational force, or Fg, plus the normal force, which is F sub n, and of course our other force due to the acceleration of the elevator, which I will designate as F is equals F sub AE, which is of course equal to 0. Why is it equal to 0? It's because the person is still standing still on the elevator and it's not moving up and down. It's only the elevator that is moving downward. So sum of all the forces there is still 0. So therefore, this is now our general equation for this particular example. So using this equation, we can now calculate the normal force that is acting for each of the cases being asked here for the problem. For example, A. During this acceleration, what is her weight and what does the scale read? So we can now calculate letter A. So for letter A, it's like this. So letter A, you need to get the normal force using this equation from here. So our equation now would be F sub n plus F sub g plus F sub a e is equal to 0. And of course, we know that by transposition, we can get F sub n, which is equal to negative F sub g minus F sub a e. Okay? So this will now be our new equation for this. So to calculate this, all we need to do is just substitute the value here. So F sub n is equal to, you know that our Fg here is, of course, that is going downward because that is your weight. So technically this is already a negative sign number here. Let me just not forget, so that you won't forget this, that I will designate this force of gravity is in the negative direction to indicate that it is always pointing downward. So therefore, using this and substituting this will become negative, and then another negative sign here, which is 637 newtons. Okay? Minus our force of acceleration due to the elevator, in which we calculate this as your mass, which is 65 kilograms, times your acceleration due to the elevator, which is 1.96 meter per second squared. 1.96 meter per second squared. Okay? There. So F sub n right now would be negative times negative, that is positive. So this will become 637 newtons minus, in this case, 65 kilograms. So that is 65 kilograms times 1.96. So let's just calculate that a little bit right now. Okay, so let's transfer this here. So 65 times 1.96 there is equal to 127.4. Okay, So this is 127.4 newtons. Okay? So that is now 127.4 newtons. Okay? So our F sub n here, therefore, would be equal to our, okay, so this would be equal to 637 minus 127.4. So if we are going to calculate that, 637 minus 127.4, that is 509.6 newtons. So that is 509.6 newtons. So this is 509.6 newtons. Okay, this is now our normal force felt by our weighing scale. Take note of that. This is the normal force felt by our weighing scale. So if that is the force felt by our weighing scale, then if I'm going to convert this into mass, this would be equal to, mass is equal to 5, that would be normal force divided by your acceleration due to gravity, which is g. So what we are going to do now is just divide 509.6 newtons to 9.8 meter per second square. So the mass that will be felt by your weighing scale due to this normal force here as the elevator goes downward would be, let's divide that, 509.6 divided by 9.8. Okay, that is around 52 kilograms. Okay, so this is 52 kilograms. Okay, let's close this. Okay, that is around 52 kilograms. So this will be the weight of your person as the elevator descends downward due to the acceleration of the elevator. So what can we say about this? So technically speaking, class, if you are descending downward with an acceleration that is of course constant, then technically you will feel that your weight is actually getting lesser and lesser. Okay, it's because that is due to the acceleration of the elevator. Okay, so from 65 kilograms you will feel like you are 52 kilograms as you descend downward. That is if the acceleration is constant. Okay, now what if for letter B, you are asked here for letter B that what if the elevator was not actually moving in a constant acceleration, but instead it's moving at a constant velocity? Because according to the problem here, what does the scale read when the elevator descends at a constant speed of 2 meters per second? Okay, so if the acceleration, if the motion is constant, remember, if the motion is at constant velocity or speed, then technically there is zero acceleration. So if there is zero acceleration, therefore the net force due to the acceleration of the elevator would also be 65 kilograms times, since there is zero acceleration here, so therefore the net force due to the acceleration due to elevator is also equal to 0. So there would be a zero net force on the force due to the acceleration of the elevator here. So what will happen is that if the elevator is moving with a constant speed, its weight would still be equal to that of mass times your acceleration due to gravity, in which in this case 65 kilograms times 9.8, we calculated this a while ago, meters per second squared, it's still equal to 637 newtons. So what does this imply? You will not feel any weightlessness if the elevator is traveling at a constant speed. You will only feel weightlessness if there is an acceleration, because if there is an acceleration, then technically there is a net force due to the elevator's acceleration. Okay? And I hope that you have learned something out from this example here for our case number 5. And that's it, my dear folks, for the lesson for today. And I hope that you have learned something out from our discussion on the concept of weight, force of gravity, and the normal force, and its application using the dynamics of Newton's laws of motion. So stay tuned for more videos. For our next lesson, we will be tackling about problem solving involving free body diagram using the dynamics of Newton's laws of motion. So see you once again for our next episode of A Moment of Science with Mr. Rabino. Bye!